The next speaker is Doriann Albertin, and the title of his talk is Type Cones of Permutory Fans. Okay, go ahead.
Sorry, I had trouble unmuting myself. Here we go. So I'm going to talk to you about permutory fans, type cones of permutory fans. This is a joint work with Vincent Pilot and Julian Ritter. So let's dig in. So first, I'm going to introduce you to what is a fan and what is the braid fan and what we can say about its type cone. So a fan is classically defined as a collection of cones that fit together nicely. So here's an example of a fan with one zero-dimensional cone in the middle, 5 one-dimensional cones that we call rays arranged around this, and 5 two-dimensional cones. Now, these are sometimes closely related to polytopes. Like, take, for instance, this pentagon here, this gray pentagon, and take one of its facets. The outer cone associated to normal outer cone associated to this facet is just the ray spanned by a normal vector of this facet. If you take a face that is not a facet of this polytope, say this vertex, for instance, then the normal outer cone associated to it is spanned by all the rays, all the normals to the facets containing this vertex. So here, this two-dimensional cone. Now, if you put together all the normal outer cones of the faces of this polytope, then you recover a fan that is the normal outer fan of this polytope, and we will say that this polytope is realizing the fan. Now, the fundamental example from which we'll work is the braid fan. Now, to build a braid fan, you need first to consider all hyperplanes xy equal to xj for I and j ranging between 1 and n. So for n equal to 3, you get this three-dimensional picture, but this has a one-dimension linearity space. So to cancel this out, you just intersect this with a normal hyperplane, and you get a picture that's more like this one. And we'll go over the labelings a little later. Now we're going to want to work on some bigger examples than n equal to 3. So I just use one little trick. So this is a braid fan for n equal to 4, and this is quite complicated to look at, to draw pictures or to have intuition. So what we do is we intersect this braid fan with the unit sphere and then stereographically project it onto the plane. And this will be much easier to make drawings or have intuitions. So just to make this clear, a chamber maximal dimensional cone here will map into a triangle, sort of, and any hyperplane will map into a circle. Now, the braid fan can be realized by a well-known polytope called the permutohedron. It is classically defined as the convex hull of points associated to permutations. So two-dimensional permutohedron looks like this, and its normal outer fan is the braid fan, like this. And now we have a real nice correspondence between elements of the braid fan and the permutohedron, and with some combinatorics. For instance, the chambers of the braid fan are in bijection with the vertices of the permutohedron. That's as usual. And these are in bijection with permutations. Here it's kind of obvious, and here you can see this by thinking that all the points in this chamber are the points of space where the coordinates are in relative order 3, 1, 2. Now, on the other side of the structure, the rays of the braid fan are in bijection with facets of the permutohedron, and the combinatorial object is ordered by partitions. Where here in red, we put only the first parts of the bipartition. Well, in general, you can say that a k-dimensional cone of the braid fan corresponds to n minus k minus one dimensional phase and to an ordered partition in k plus one parts. Now, the question is, once you get a fan that can be realized, a polytopic fan, what are all the polytopes that realize it? And first step to answering this question is the definition of Macmillan in 73 of the type cone. The type cone will basically be the formalization of this question. It is all the type cone of a fan is morally all the polytopes that realize this fan. And I will explain on an example, it will be much easier. So you take your favorite fan, and then you pick a ray, say the ray 3, and you to build a polytope whose normal arc of fan is this fan, you will need to have a facet corresponding to this ray. So you pick just a distance from the origin, a height along the ray 3, and this is where you'll put a hyperplane to define a half space. And you do this for all rays. You get 6 half spaces, and you look at this intersection. And if in this case, the intersection normal outer fan, sorry, is this fan, so this choice of H vector is in the type cone. Had we chosen H13 to be slightly bigger, like this, which is past this crossing here, we'd get a pentagon whose normal outer fan has only 5 rays, so it could not be this one. And so this choice of H is not in the type cone. Now, how do we compute a type cone? We will use a proposition from Chapoton, Famine, and Zedevinsky that assumes that the fan that we look at is simplicial and has some other properties that we will always have in this talk, at least. And then an H vector is in the type cone if and only if it satisfies some inequalities called wall crossing inequalities. Now, what are these? So you take 2 chambers, so maximal dimensional cones, that are adjacent. So F is simplicial. So if this dimension we're living into, array as chamber as D rays, and so these 2 chambers share D-1 rays here, and they have +1 ray that on their own each. So by a dimension argument, there is a unique linear dependence among all these rays up to scaling. And the wall crossing inequality associated to this pair of adjacent chambers is just take this dependence and replace the rays with the height you want to take along these rays, and ask for this to be strictly positive. So type cones is completely determined by this big family of inequations. The idea is that if you don't, if this property is not verified, the fan you will look at will look more like this than like this. Now, in the case of the braid fan, this is well known. Once you've taken an adequate set of representatives for the rays, you have this inequality, this equality. Sorry, this is a relation between rays, and so the corresponding inequalities are those, and the type cone of the braid fan is completely determined by those that we call submodular inequalities. Now, this is nice, but this is not perfect because we have some redundancies. In this big family of inequalities, some are implied by others. So we have a slightly better statement, that is that the type cone is completely determined by the submodular inequalities satisfying this relation, and all of them are necessary. So these all define a facet in the type cone. We call the type cone is a polyhedral cone, so it has facets, and these are the all submodular inequalities, submodular inequalities that satisfy this proposition, this property, are exactly the one that defines facets. Now, if we go back to our example, if you take I equal 1 and j equals 3, there is a submodular inequality h1 plus h3 should be bigger than h1 and 3. And this is exactly the condition that we break when we push h1 3 slightly too far on the right. To finish with this part, I'd like to show you a real nice picture from the short polytope article of Padrol, Pilot, and Ritter, where we see a section of the type cone of the braid fan for n equal 3, which is nice enough to live in dimension 3. So the type cone is actually the section of the type cone is actually interior of this polytope, where everything looks like a sort of hexagon with various shapes. And as soon as you push your point to touch a facet of the section, it means that you have pushed one hyperplane slightly too far and changed the combinatorics of the polytope. So this is type cone. Now I will introduce you to the one thing that we're interested in, so the permetries and the associated polytopes. So a permit tree is a planar-oriented tree on n inner nodes, labeled from 1 to n. Each node should have either one or two. Each inner node should have either one or two parents and one or two children. And there is a constraint on the labels. If our node has two children, then we put a red line beneath it to symbolize the fact that everyone in the left subtree should have a smaller label, and everyone in the right subtree should have a big label. Same goes if you have two parents, everyone in the left parent subtree should have smaller labels, and everyone in the right parent subtree should have bigger labels. So here's an example of a nondescript permit tree. And what we want to do with permit trees is record the shapes of the nodes. So here's down, up, none, both, none, down, up. And we call this recording the decoration of the permit tree. Now, in general, we will look at families of permit tree with a given decoration. And the reason why permit trees are so interesting is because they interpolate between already known, very interesting combinatorial families. For instance, if you force the decoration to be only non-shaped nodes, the families of permit trees you'll get will be in bijection with permutations. Here is the permutation 2, 7, 5, 1, 3, 4, 6, for instance. If you force the decoration to be all down-shaped, you will get a family of permit tree in bijection with binary trees. Now, what we are interested in with the permit trees is the following. You fix the decoration, say the binary tree one, and then to any delta permit tree, you look at all its linear extensions. So say this tree, for instance, is labeled 1, 2, 3, and you orient it from bottom to top. And so this is already a linear order. And so the only linear extension is 1, 2, 3. On the other hand, if you look at this one, you may choose whether you put 1 higher than 3 or 3 higher than 1. So this, seen as a bow set, has two linear extensions, 1, 3, 2, and 3, 1, 2. So this yields an equivalence relation on permutations. And what we want to do is look at the braid fan and then glue together the chambers of the same equivalence class, of same permit tree. So 3, 1, 2, and 1, 3, 2 have the same permit tree. So we just glue together this two chamber in a bigger one. Now observe that doing so, we get what we call the delta permit tree fan. Well, it's a fan, it's not obvious. PON wants to prove this. But observe that we lost the ray 1, 3. We have a smaller amount of rays on the right in the delta permit tree. On a bigger example that will follow us for the rest of the talk, none, none, bottom, not none, sorry. you can look at this parameter tree, for instance, where you can choose between 2 and 4, which one's the highest. And so you get two linear extensions, 2, 4, 3, 1, and 4, 2, 3, 1. These are this permutation and this permutation. And so we glue together these two chambers here to get this big chamber here. And along the way, again, we lost some rays. For instance, 2, 4 here used to be a ray of the braid fan, but is not a ray of the delta parametry for this choice of delta. Now, it so happens that delta parametry fans are polytopic, and so here's a proof, sketch of proof. If you take the set of rays of the delta parametry fan, the one that we did not lose, you can build a polytope out of the inequalities of the permutahedron by selecting only those corresponding to rays in I delta. Or if you took it the other way around, you can start with the permutahedron and then remove all faces, all facets in equations corresponding to rays that we lost while building the delta parametry fan. Now, what you get is an H vector, and you just have to check the wall crossing inequalities for the delta parametry fan, and this yields the result. Now, this result specializes well for permutations in binary trees, where we recover the permutahedron, of course, and low days associahedron. So this is the delta parametry corresponding to the delta parametry fan we had before, where every vertex is labeled by a parametry. Now, call remove-ahedron a polytope obtained in such a way, selecting a subset of facet-defined inequalities of the permutahedron. It was it is clear that parametry fans are remove-ahedral. They are realized by a remove-ahedra. John? But we prove that they are in fact strongly remove-ahedral, meaning that you can replace here the permutahedron by any polytope realizing the braid fan, anything in the type cone of the braid fan. And this is still true. So they are strongly remove-ahedral. And we prove another statement concerning remove-ahedra, meaning that among the bigger class of quotient fans, which is a bigger class than parametry fans, the only ones that are remove-ahedral are the parametry fans. If you do not know what a quotient fan is, or if it interests you, you just have to wait until the next talk where Doriann will most likely talk about quotient fans. Okay, so now I'm able to state what I want to say about the type cones of the parametry fan. So recall we had the Shaperton-Femin-Zelevinsky proposition that states that we only need the wall crossing inequalities. So first thing we have to do is find out which are the rays of the delta parametry fan. And then we need to know which one define an inequality and a strict inequality, one that is not implied by the others. So we have a nice combinatorial way of seeing the rays of the delta parametry fan. So the ray of the parametry fan is a ray of the braid fan is a ray of the delta parametry fan, if and only if it is an edge cut of some delta parametry. This was known from Pilot and Ponce's parametry article, but we got a nicer combinatorial way of seeing it that I will explain on an example. If you take the ray 1, 3, 4 for n equal to 5, just put 5 dots in a line and color red the ones in I and blue the others, and then link them together, passing below points in blue and above points in red. Now, the only thing you need to have on the decoration for I to be a ray of the associated fan is that whenever there's someone passing below a point, you do not want this point to have a down fork. So you can have either an up or a none here. And conversely, here there's someone passing above at this point. So you can have either bottom or none, but not in something with a fork looking up. Again, this specializes in the case of the permutations, we get back all the rays. That's reassuring. And in the case of the binary trees, we get all intervals. Now, if we go back to our example, we are able to compute easily all the rays that we keep in here. And recall that we lost this 2,4 here array, and we can check it is indeed not in I delta. So doing the same drawing, we get this thing because the array is 2,4. And at this point, the decoration is a bottom down, so it has a down 4. It pierces this arc here, so 2,4 is not an I delta indeed. Now, we have as well like combinatorial characterizations of the wall crossing inequalities, the pairs of rays that define facets of the type cone. I will not dig into the details because it's not that good looking, not that bad looking either, but well, I won't go into the details. Just know that we have the nice combinatorial characterization. And this specializes again. We recover, of course, for permutations, the submodular inequalities with this property. And in the case of the binary trees, we get a very similar condition. Actually, you can write it down in the exact same way. We looking at curve intervals that only differ under extremities. So the condition is actually the same. Now, if we go back to our example, we can again compute all of the pairs of rays defining facets of the type cone. And for instance, here you can look at 4 and 2, 3. They define a pair of adjacent regions, this one and the big one here. But they do not define facets of the type cone. They're not in this list. This means that the corresponding inequality can be written as a sum, a linear combination of the inequalities defined by these pairs of rays. On the other hand, 2, 3 and 3, 4 define as well wall crossing inequality, and it is right here. So this one is necessary, defines the facet of the type cone. One last remark, one last thing I want to point out is that this allows us to get some nice counting formulas for the number of rays of the permutree fan and the number of facets of the type cone. So recall the number of rays is the number of faces of facets of the underlying polytope. This specializes still to quantities that were already known, so again, reassuring. And this allows us to state, to know when the type cone is simplicial. So we have an if and only if condition. Let's say that the type cone is simplicial, if and only if the permutations are not of this shape. The decoration, sorry.
Have you said what that omega, excuse me, have you said what that omega is in that formula? Did you define it before?
No, I've not defined this omega. I'll be honest, this is just to show you that I have some, I have a nice way of counting this. This is not very complicated, but this takes some space, and this is not what I want to talk about. I just want to say I have a counting formula. So just a little leap of faith here. Okay. So yes, we can know when the type cone is simplicial. So that's all I wanted to say. Now I just want to open up to some perspective. There are a lot of ways you can glue together chambers of the braid fan to get another fan that is polytopal. Among these many ways, the cushion fans are a very interesting one, and we have some good results on them, but we still don't know exactly what their type cones look like. So this would be something to look at. And to conclude, I'd just like to show you this nice picture from the permutree article, where you can see all the permutrees for n equal 4. And thank you for your attention.
Thank you. And do we have questions?
Hi, Doriann. I have a question.
Yes.
So I want to ask, so here you have 4 power n possible decorations, right? For
Yes.
any given n. And so for large enough n, is it true that the 4 power n permutory hadrons that you get from each of these decorations, they are different as polytopes?
So first thing is you don't really care about the first and last decoration. If you look at this picture, well, it's a little small, maybe I can zoom in. If you look at this picture, the first and last one are always none, because these actually don't play any role in the combinatorics. So actually it have 4 to the n-2. So that's the first remark. Second remark is you have some symmetries, of course. Down and both will be symmetric to up and both, and to both and down, and to both and up. The symmetries, vertical and horizontal, of the decorations translate into symmetries of the permutory hedra. Now, I would tend to believe that these are the only symmetries you'd get, but I'm not 100% sure, maybe 80%.
Okay, thank you. So do you know if for example, if you can obtain the permutahedron from some other decoration, or the associahedron from some other decoration?
Yes. So the permutahedron is right there. It corresponds to all non-shaped. You recover everything. You don't change anything. And you get the permutahedron, and the associahedron is with both down. It's right there. This is...
So what I mean is, so I mean, is there some other decoration for using which you can obtain the permutahedron?
No, this would be the only one, because if you take any other one, you will lose some rays.
Okay.
And to get the associahedron, you have a second one that is up and up, because of course it's symmetric.
Okay.
But
okay.
no, I don't. There's no other ways to find it in this scheme.
Okay. Thank you.
Other questions? Okay, so thank you, Doriann, for a very nice talk. We have a